Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. We're looking at subsection 223. Okay, so we're going to be looking at another way of thinking about union and intersection. And notice that we have this other symbol here, which is kind of like a logical or. Or sometimes you could think of in a post set or a partial order, you would say it's a join. Um, so P join Q, or you could say P or Q, P union Q. Okay, so what what is it and what does it mean? Well, essentially, if we're looking at least in a post set type of way, P union Q or P or Q or P join Q, say, so P join Q is the smallest object in this partial order that's ahead of or above both P and Q. So it has to be both above P and Q, and it's the smallest one down. And that means that if anything else at all is above both P and Q, then this guy is actually below it. It's below it. So, so this diagram says exactly what this means. So it follows this particular kind of minimality property of being above both P and Q, and anything that is above both P and Q, it's going to be below it. So that's, and actually that works perfectly for unions, because we're not going to be adding any extra elements to in a union, but it is definitely bigger than P and Q, and anything that's above that contains P and Q, both as subsets, will contain the union of the two. So it works well for power sets when we think about that. But this idea of meet or join, well, in this case, join, works well for other settings other than just power sets. And we're going to be looking at an example of that. But first, before we look at that, we're going to introduce the idea of a Hasse diagram. So a Hasse diagram is a diagram that allows us to think about things minimally in a post set. So if so in a post set, we have the idea of transitivity, for instance. If there's an arrow that goes from Q to from Q to here, then definitely there's an arrow that goes from here to here, right? So we don't have to draw the arrow from here to here, because we already know we have this path. So if we draw this path, we can just assume there's an arrow from there to there. So it's kind of a minimal picture that if we just kind of thought, oh yeah, since we have a path there, we have a path here, then we don't have to draw all the arrows, right? In fact, if we assume it's a post set, we also know that it's reflexive, so we won't have to draw that in. We don't need to draw in any self arrows. And we also know that it's and anti-symmetry is, well, that's a property of how we've kind of drawn our arrows in this particular case. So really, we're just kind of dropping all of the self arrows, and then right here, we're just looking at drawing only the maximal path from one thing to another, and that's it. So only draw the maximal length path, not any shorter paths at all. And that would be what you would call a Hasse diagram for a post set. And these are very nice to use at times when we're going to be considering pictures and diagrams of power sets and logic and other things like that. Would be very useful. Well, while we're on this vein, let's take a look at another example of a post set. So these don't look like subsets at the moment, do they? But instead, actually, these are factors of. Like 1 is a factor of 5, 5 is a factor of 10, 10 is a factor of 30, 30 is a factor of 60. These are all, so these arrows mean is a factor of. I mean, you could, but you could think about these things as being subsets. If you picture every number right here, like 15, if you picture 15 as being a set, the set of all of its factors, its positive factors here. So itself, 3, 5, 1. If you thought of that as a set, then definitely all those factors are also factors of 30. So this could be thought of as a subset. Kind of nice. Okay. So you could think of these arrows as being a subset, but it's not exactly a power set. There's some things missing, but it still is a partial order. It meets all the criteria for being a partial order of transitivity, reflexivity, and anti-symmetry as well. Okay. So, and this actually is a Hasse diagram. Just like we had, so this is a Hasse diagram. Why? Well, let's see. If we have all the relationships can be determined from this picture. There's not an arrow that goes directly from 1 to 15, but we know since there's a path that we can assume there is one. So we've kind of only drawn the maximal paths, and this is an example of a Hasse diagram. If you have a Hasse diagram, you can actually see joins, which are kind of like the unions, very nicely. So for instance, if we want to find the join of 2 and 5, we find the lowest thing that's above both of them. Well, 10 is above both of them, and that's the lowest thing. Anything that is above both 2 and 5, 30 is above both 2 and 5. Look, 10's below it as well. It meets that property. So 10 is kind of like the join of 2 and 5. But we wouldn't say that it's the union of the sets 2 and 5 necessarily, because notice that set 10 actually has 10 in it, but the sets for 2 and 5 don't. So it's actually not even a union. It actually, you could actually, it contains the union, but it is not the union. It's a little bit more than it. So, but in this particular post set, it is the join, you could say. So you say join instead of union because it's a different type of partial order than a power set. Union is the join for power sets. So if it's a power set, then you can say union. But other than that, the more generic term is join. All right. So, and this discusses what we just talked about with that subset, and that. Okay. All right. So that's join. Now, what about this symbol? All right. If the upside down symbol for the join, this means highest below both. So here you can check on the Hasse diagram that for, and then actually we, instead of meet, we say join. For join 30 is equal to 2. Well, let's see. Let's look at the Hasse diagram to see. So what's the lowest thing below both 4? Or the biggest thing, I guess. The biggest thing that's below both 4 and 30. And we'll see that it's actually 2. 2 is the biggest thing below both 4 and 30. What's the biggest thing below both 6 and 2? Both of them, well, it's just 2. 2 is below itself because of reflexivity. You have to remember that. Okay, so for a partial order. So it's kind of like the idea of greatest common factor or least common multiple, actually in this post set. So factorization post sets. So meets and joins actually take on the wording of, instead of union and intersection, they take on the wording of either greatest common factor or least common multiple. Least common multiple is the join, or kind of like instead of the union. And greatest common factor is like the intersection or the meet. But often in logic, we're not even going to use the word meet and join, although we will borrow the symbol for meet and join. That's where it comes from. So these symbols we'll use, but we'll think of them as or for union, and then we'll think of them, and then this as and for um, meet, okay, or intersection. All right, now let's look at this example of a okay, so this is a power set. We're going to look at the Hasse diagram of this power set of the collection 1, 2, 3. All right, so this is a Hasse diagram. Notice it has just a minimal amount shown, but yet all the relationships are present here. Okay, so what is this? 2 join 3, which is the same thing as, well, join is the same thing as union, so it's just 2, 3, right? And 2, 3, right, is the smallest thing that's below both, that's above, smallest thing that's above both 2 and 3 in there. All right. Hey, now let's look at a very simple power set. This one, the empty set and 1. This is a Hasse diagram for the power set of a singleton set just with one thing in it. All right, the binary code for this is easy. It's just, this is one position because there's one element, it's either 0 or 1. In fact, we could just represent this by codes completely. So 0, 1, like this. Now, in this little Hasse diagram, there's a nice operation. Just looking at this Hasse diagram using join and meet, or you could say or and here we go. Let's look at it a little bit. So what's the biggest thing below 0 and 1? Below 0 and 1, well, reflexivity is 0 because there's an arrow going back to 0. What's the lowest thing below both 0 and 0? It's 0. What's the lowest thing below? What's the biggest? Sorry. What's the biggest thing below 0 and 0? Okay. What's the biggest thing that's below both 1 and 1? Well, 1 itself by reflexivity. What's the smallest thing that's above both 0 and 1? Well, 1 itself. What's the smallest thing above both 0 and 0? By reflexivity, so above 0 is above itself, is 0. What's the smallest thing below both 1 and 1? Well, just 1 itself. So, but this is also like, you could think of this as like, think of 0 as like empty set because that's really what it represents. And 1 is like being a whole set, whether singleton or whatever. And this makes perfect sense. This is intersection. Empty intersect with set is empty. Empty intersect with empty is empty. One whole set intersect with whole set is the whole set. Empty union with the whole set is the whole set. Empty union empty is empty. And whole set union whole set is whole set. So or and union intersection, it all matches and agrees. In fact, this is kind of the key and crux for something called Boolean algebra, which we'll be working with. And this is a neat description where it comes from and how to work with it, how to think about it. Thanks for watching.